everybody, and welcome to York University Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and as Paul would say, the darn good friends of York University. I am going to be one of your hosts this evening. My name is Jesse Rogerson. I'm joined by Ryan.
Good evening to those around the world.
And Kshitij.
Hey, everyone.
And we, of course, for our loyal listeners, we're broadcasting live from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. And what you are hearing is the beginning of Astronomy Night in Canada, where the entire lineup on AFM is Canadian. And it starts with us, York Universe. I'm a little biased. I think we're pretty good. But then it goes on to Western Worlds, Quirks and Quarks, and Science for the People. Those three programs are incredibly good listening. So if you have time, stick around for those. York Universe, we come every Monday night at 9 p.m. local Toronto time, or Tuesday morning, 2 a.m. UT, if you're going with Universal Coordinated Time. York Universe production, we work in concert with the online public viewing program that the observatory team runs, which is running from 9 p.m. to 10 p.m. local Toronto time. If you want to get involved in that, you want to go to the observatory.info.yorku.ca, and you can go and see what they're up to. Last time I checked, the skies in Toronto were patchy at best, so I'm not 100% certain what's going on in the observatory tonight.
Patchy would be nice this season, yes. Let me tell you.
And you're listening to this broadcast powered by AFM, right? They're the voice of astronomy. And if you ever have any questions or comments about this show, you should find a way to get in contact us with. We're on Instagram, we're on Twitter, we have Facebook pages, we're on YouTube. You can find us. Look for us and you can find us. Okay, everybody. It's been a while for me since I've been on here. How are the two of you two doing tonight?
Kshitij, I'm really curious how you're doing, my friend. How's life treating you?
I wouldn't complain. I mean, of course, I cannot complain. I wouldn't complain. I'm on the West Coast, and I'm still without a job. Oh yeah, so that's the funny part. And I got like dark skies, like real dark skies.
Oh wow!
Of course, there's light, of course, but then so that's evening for me. That's why I have a frappe, and that's as good as it gets.
What you said? You got a job? What's your job?
No, I didn't get a job. That's what I'm saying. So, like I said, I'm not complaining still because I still have my science to read and stuff to do and think and all that. So yeah, but trying to survive.
Oh, that's excellent. I mean, it's even worse for an astronomer on the West Coast than it is in Central Ontario. There's even more rain and cloudy skies compared to where we are in Toronto. So yeah, I think you're just. I mean, it's a terrible place. Canada's a tough place for an astronomer. This is one thing I talked about the last time I was on, about a month ago or so, and it was like, in the winter, it's great because it gets dark so early and you can go outside early and right after the sun sets at 4:00, but it's cloudy because it's winter. And it rains and snows and sleet and hail and everything in between. And then, finally the weather clears up. It gets nice, it gets sunny, it gets warm, and then the sun doesn't set till 9:30. It doesn't get dark till 11. So I heard, there's no winning.
So here's a good question, right? Is where is the best possible place to observe from in Canada? Meaning, balance a few things, those mostly being, where are you going to get the most clear skies and on any season, really? Now, I heard, because I lived in Calgary for a while, and when I lived there, Calgary was very in my face about telling me that it was the sunniest place in Canada. And that for some reason they have the least clouds around. I don't know if that's true, but I do remember being there and living in Calgary. It was actually pretty blue skies most of the time, surprisingly.
Well, they're on the leeward side of the Rockies, right?
That's right. Mm-hmm.
They should. That should help. I would have said something like the furthest northern point in Canada, basically the North Pole, because of the continuous darkness that they can get.
Right, but that's only for 6 months. I mean, you're going to have 6 months of time where you're in like perpetual twilight or daytime.
This is true. Yeah.
I think based on the little experience that I have, of course, it's very, very little, but I can only compare the East and the West Coast. Maybe Toronto is still the best option, considering all sorts of
Interesting.
I don't know. I mean, resources, because on the West Coast, you do have the summer months, which are clean quite a few days. But if you look at the winter, it's always raining, I think.
Oh yeah, the summer months in BC are like 2 weeks. There's like 2 weeks of summer in Vancouver, and it's clear and it's beautiful, and then it just goes back to rain for the next 11 months. So, but
now,
see, I was thinking too, the cloud cover disappears as it gets colder. So far north, let me tell you.
Yeah, you're probably right. Yeah, and aren't there some like telescope projects up there?
Sorry,
I think so. I'm not sure though.
Okay. We should dive in. We got lots of cool stuff to talk about today, and of course, for those that are our loyal listeners, they'll know that we start off the show every week with This Week in Space and Astronomy History. And for this, we're going to start with Ryan. He's got a really cool astronomer to talk to us about. Yeah,
honestly, he's one of my favorite astronomers, especially being fairly modern. It's Gerhard Kuiper. He was born December 7th in 1905, and he was born to a family of tailors in North Holland, so he's Dutch by nationality. We, of course, know the name Kuiper when we say the Kuiper Belt. Any astronomer knows about the Kuiper Belt, the icy bodies farther out in our solar system, past Neptune, and infamously part of the reason that Pluto is no longer considered a planet. But he was known to have really sharp eyesight. I think most people on a good day can spot, in a perfectly dark skies, could spot an object about 6th magnitude with the naked eye. It was said, maybe the legend of Kuiper, that he could spot something at magnitude 7.5. So about 50 times dimmer, I suppose, if I'm doing the math right, which I'm probably not. It's a little late for me. I'll get Jesse to confirm my math. 1.5 magnitudes dimmer. So there you go. Anyway,
I can't do it in my head.
I know, right? So, listeners, tweet me at Astroinactions. He studied at Leiden University and was known to have actually mentored a lot of very well-known astronomers, including Jan Oort of the Oort cloud fame, and Einar Hertzsprung. Co-founder of the Hertzsprung-Russell diagram of stellar classification. And I also know that Kuiper was a mentor to Carl Sagan, often considered the greatest science communicator of all time.
I did hear that myself, yes.
So Kuiper himself, he discovered moons of Uranus and Neptune, a CO2 signature in the Martian atmosphere, some of the thick atmosphere over Titan. He pioneered airborne infrared observing using aircraft in the 1960s and actually helped identify landing sites on the moon. But my favorite anecdote about Gerhard Kuiper is that when he was talking to Neil Armstrong before Armstrong went up to the moon, and Kuiper was assisting with the selection of lunar landing sites, he said to Neil that the moon, when he steps on it, would feel like crunchy snow on a cold morning. And so, sure enough, Neil Armstrong went and walked on the moon. And when he came back, he told Kuiper that Kuiper was right, that it did feel like crunchy snow on a cold morning. And so I think that's a really cool thing, because when you think about going to the moon, it's like, okay, yes, they walked on the moon. But to actually give it a feeling, like we all know at least those of us north of a certain at a certain latitude know what crunchy snow feels like to walk on, this cold, crisp morning snow. And I think that's a really amazing way to explain what the moon feels like. And it really makes it more experiential to talk about the fact that, it feels like crunchy snow. I can imagine walking there now. And Kuiper was correct. So that's one of my favorite facts about Gerhard Kuiper, a very, very famous astronomer in the modern day and the namesake of the Kuiper Belt. Happy birthday.
You know, that I was just last night we had a pretty good snow here at my place. And I don't know, Ryan, if you got that too. And it melted by like 9 a.m. It was like all gone. But like in the evening last night, it snowed pretty good. And I went out and I walked out in it because I was taking out some garbage. So that feeling of crunchy snow, because it was that like packing snow type snow that it wasn't.
Yeah, a little bit of ice rain too last night.
Very fresh in my mind. And that coupled with the movie, that movie, the biopic on Neil Armstrong with, I forget the name of the actor.
Oh, yeah.
You couple those two, because that one's pretty fresh in my mind as well. That, yeah, it makes me feel like I can almost picture what it would like to be like almost to walk on the moon. If only, eh?
Yeah. Well, who knows? As time goes on, as technology advances. Comes to fruition, maybe it won't just be observing satellites. Maybe it'll be some other stuff too that takes us to the moon.
One of the things that blows my mind about Kuiper is just how much science he touched, right? Like, so obviously, we have the Kuiper Belt named after him, right? I'm fairly certain, did he predict that it existed? I don't know. No, he didn't actually discover it because the first object wasn't discovered until like 1992 or 1980 something or whatever. But he predicted that it would exist. So that's a huge thing, right? He predicted a structure of the solar system. It's more than just like objects. It's like, this is a evolutionary structure of how the solar system formed. But then, so you have that, but not only that, but he was like hanging out and chilling with some of the greatest minds at the time. And you have he discovered moons. He worked on the atmosphere of Mars. He worked on Titan. Like, this guy was like,
he was a true observer.
How did he have so much time to like be a part of so many papers?
He was an observer. I think he had access to a really state-of-the-art telescope at the time. It's kind of the same as Hubble with Mount Wilson, right? Like, you have one of the larger telescopes at the time, and you basically just live there and observe every night. And oh man, that's the dream, right? But we don't do that as much these days. But Kuiper, I think, was in the same boat where he had control of and was operating a pretty significant telescope. I can't remember it off the top of my head, but this is also why a lot of astronomers would go and work with him, take data with him. This is why he was considered a keen observer. This is why he was so ubiquitous in a lot of planetary astronomy. Is he had the kind of telescope that would let him track these solar system bodies over many, many nights, which is basically how you discover them, right? You look at stars, a field of stars along the plane of the solar system. One of them appears to move after a couple of nights. Well, then it must be closer to us, so it's probably a solar system object. So that's one of the things that having access to a bigger telescope gives you the opportunity to, just by keeping your eyes on the skies, to learn and discover and participate in a lot more science.
Lastly, oh, sorry, go ahead.
Please.
I was just adding to this like maybe the fact that you had Carl Sagan coming up a little while later. I'm not sure that's the right way to say it, but that place might have just been the
center of astronomy.
Yeah, I mean the cradle or whatever. Yeah, that's right, but probably. But so maybe these people were meant to be there, and they did their job.
What, Ryan? When you were talking about like the legend of Gerard Kuiper, right? The 7.5 magnitude thing. So the magnitude thing is for those that don't know, is this astronomy brightness scale. Basically, it's an intensity scale where the brightest things in the sky are magnitude. And it dates back like thousands of years, and are like magnitude 0 or 1. And then the dimmest things in the sky that are visible to our eyes are usually like magnitude 6-ish. And so being able to see something dimmer than magnitude 6, right? So maybe he could see this, maybe he couldn't. But all it could make me think is that I need to get my eyes checked out like I need new glasses soon. And when I go to the doctor, I wish that instead of them telling me like, yeah, your right eye is 1 point whatever and your left eye is whatever the hell, you know how you get those like prescriptions. I wish they would tell me it in magnitude form. Like, you can see this magnitude with this eye and this magnitude with this. I feel like that's what they should do.
In perfect skies. I think everybody has terrible eyesight if you live in a city.
Yes, true. Okay, everybody, we should move on from Kuiper, the prolific observer and namesake of the Kuiper Belt, on to December 8th of 1995. And this is when the Galileo space probe entered into orbit around Jupiter. Now, the Galileo probe, for me, it wasn't a huge mission because it was sort of happening around the time that I hadn't really found my feet in astronomy yet. I was very young. I think so in 1995, I was only 10 years old. I wasn't really paying attention. For me, the mission that defined the solar system for me was the Cassini mission, because it arrived at Saturn in 2007, I think, 2008. And so that was right when I was really getting into astronomy. But if you put yourself in the frame of mind of how amazing Cassini was arriving at Saturn, that's what Galileo did for Jupiter. Galileo arrives at Jupiter and completely changes our understanding of what's going on there. The data that was sent back, the images that were sent back of the Jovian atmosphere, the storms, the great red spot, but the unbelievable images of the moons, the Io and Europa specifically. Europa, as far as I'm, if I can remember correctly, that was the mission where Europa was definitively shown to likely have a liquid ocean below its icy surface, because they got good high-res images of the ice surface of Europa, showing that it was cracking, and the cracking suggests an ocean below it, basically. So you have that. You have these amazing images of Io. So this Galileo space probe was one of the defining missions of the solar system. And the cool thing is that it did a lot before it even got there. In order to get to Jupiter, instead of flying in one straight shot, one single transfer orbit, it did a whole bunch of weird arcing orbits all over the place, basically to save fuel, do a bunch of gravity assists, and arrive at Jupiter with the right velocity. But on its way, it notably did 2 flybys of asteroids, which I believe were Gaspra and Ida, if my memory serves me. And one of them, and maybe the two of you could help me with this, one of those asteroids was found to have a moon, right?
I think
yes,
Ganymede has a moon.
It was Ida and Dactyl.
Ida and Dactyl, that's right. So
Dactyl was the tiny little moon.
Right. So this Galileo is flying through the solar system. Its ultimate mission is to get to Jupiter and learn as much about Jupiter and its moons as possible. But on the way, they're like, hey, let's fly by some asteroids because we're going to come close to them. And it flew by Ida. And Ida was shown to have its own little moonlet, its own little asteroid moon, which I believe was the first time that was ever seen. And you fast forward to today, and you can see the relevance, because today, just like a month ago, the DART mission was launched from Earth off to fly to Didymus, which is an asteroid that has its own little asteroid moonlet called Dimorphos, I think. And so that's an asteroid with a moon, and then Ida and Dactyl, asteroid and moon. So it was changing. The Galileo probe was, changing understanding all over the place. It wasn't just Jupiter. It was what asteroids are like. And, of course, what it did for the moons was insane. And, of course, by the end of the mission, which I think was in the early 2000s, 2001, 2002, maybe 2003, Galileo was running out of fuel and, used this fuel to change its orbits so it could do flybys of the moons and get closer to Jupiter and so on and so forth. It was sort of running out of fuel. And, of course, to be super, super safe, just to make sure that Galileo wouldn't land or crash land on Europa, which is now seemingly like one of those places in the solar system that would be really good for life given all the water that's there. You don't want to contaminate Europa, so that it was deorbited on purpose into Jupiter, where it burned up in the upper atmosphere. And that's the end of the Galileo spacecraft, and one of the most important and amazing fact-finding missions that has ever happened in the solar system.
Jesse, you were talking about when it was on its way. One of the really cool things it did on the way as well was it flew. So 1994, it was Comet Shoemaker-Levy 9 that crashed into Jupiter.
Yeah,
and
right.
Galileo was on the way, and sure enough, saw from its own perspective that collision happen over a period of 36 hours or however long it took for all the pieces of Shoemaker-Levy 9 to crash in. So I thought that was kind of interesting because it was right around that time. And then sure enough, it's like going to Jupiter. And that was like, this amazing bright explosion that everybody on Earth watched. I didn't. I was 9.
Yeah, I missed it.
But it was kind of cool to think about, right? So yeah, I thought that was a really neat one too, is that it was able to do science while on the way, right? A lot of missions today, especially, they're packed up, the instruments are protected. It's like, okay, we're going to send it, and when it gets there, we'll open everything up, turn it on, and let's hope it works after doing tests or whatever in low Earth orbit. But in the case of Galileo, it was like, okay, well, we can do science with every single second of this mission on the way, when it gets there, before it deorbits, as long as it still gets funding. And so they did, and I thought that was really cool that they were able to observe Shoemaker
I think
leaving
it was
out.
like, wasn't it like it was pretty close. It was like a month before arriving or 2 months before arriving or something like that. It was
Yeah. When did it arrive?
So that was December 8th, 1995 is when it arrived at Jupiter to go into orbit around Jupiter.
Trying to remember.
And I can't remember the Shoemaker. And hey, didn't Jupiter just get smacked with like just recently by a couple of small little things?
I did hear that.
There's been more than one sightings of that. That was like 2 weeks ago, actually.
Yeah, right. Not nearly as big as Shoemaker Levy 9, but
July collided with Jupiter. So July 94, and then I guess December 94.
No, December 95. So it was actually
95.
It was still a year away. Oh, okay.
Yeah, okay. Well, I mean, that's still more than halfway, so.
It's still closer than we are.
Yeah, definitely, right?
You don't want to be that close.
One of the things that I like about Galileo is, like I said at the very beginning of this, is like Cassini really defined the solar system for me, because that was a mission that was arriving at Saturn when I was starting into my astronomy role, my astronomy career, and just trying to put myself in that frame of mind, because Cassini completely changed our understanding of Saturn. Beautiful images, and Galileo was exactly the same thing. And I'm looking, and Juno is at at Jupiter right now, and there's another mission flying off to Jupiter, all following in the footsteps of what Galileo did. What a great mission. Okay, we should move on to the next one. We're already at 9:20. We got stuff to talk about. So, Kshitij, you're going to tell us about the Icarus Japanese spacecraft.
Sure, I'm going to start. So, December 8th, 2010 is when Icarus had been launched. Before that, of course. This date, 2010, it did a flyby, the closest or nearest approach of Venus. And the nearest approach distance was 80,800 kilometers, which I think is pretty close for something that far. Yeah, and it is said that the mission continued past the end date. And they say, the mission control said that there was an attempt to enhance the control of solar sail equipment, or solar sail in general. And it's been recognized by the Guinness Book of World Records, or Guinness World Records, whatever you call them, as the first successful solar sail mission, sort of. And I think, Jesse, you were saying you would probably have hands-on things to talk about, like not hands-on on the mission.
Yeah. The Icarus mission, it's such a cool mission. So this was launched by the Japanese. There's JAXA, the Japanese Aerospace Exploration Agency, I think is what it stands for.
Yes.
And so it's a solar sail mission. The Japanese were like, hey, let's see if we can make a solar sail work. And a solar sail, all it is a big, huge, massive sail, just like a sailboat. But I can't remember what material it's made of, but it's a really big, it's 14 meters by 14 meters. Think about how big 14 meters is. That's like almost the size of a basketball court, right? This thing is huge, but it's incredibly thin. It's like way thinner than a piece of paper. Like it has to be thin, because if you had a sail that big and it was a thick sail, then it would weigh like a ridiculous amount of weight, and you can't have it weigh, because what the way a solar sail works is a photon that comes from the sun, hits, and it does a momentum transfer. The photon basically is colliding like billiard balls collide, and then transfers momentum to the sail, and then the sail uses that as its propulsion. There's no rocket on board. There's no thruster on board. Its propulsion is being hit by photons. And they wanted to see if they could fly through the solar system using solar sail technology. And so in 2010, they demonstrated quite convincingly that they could do this because they flew from Earth to Venus, and they got to within 80,000 kilometers of Venus, which is super close.
Cool.
And demonstrated fully that a solar sail technology is definitely viable. There are downsides to solar sail technology because it's not easy to transport like a large payload. Like if you wanted to send if you wanted to use solar sail technology for humans, say to like send a spacecraft full of humans somewhere, well, you'd need a solar sail like 10 times bigger or 100 times bigger or something like that.
And then how do you get that into orbit too, right?
Yeah, well, who knows, right? So there's big issues with this. But
and then you can mention that this particular satellite itself was 300 kilograms, which is anyways heavy enough for your dynamics to work.
300 kilograms, that's all it was, eh?
That's what it says. I mean,
wow.
That's
light.
That's light? Okay.
Well, I mean, it's heavy, it's heavier than a person, but
as far as spacecraft go, it's light. But
yeah, exactly. That's as big as any random spacecraft. But you couldn't, if you wanted to fly humans, if you think about it from a human perspective, if you want to go back and forth from Mars, for instance, we're still not sure. Ryan, you point out if you need a big, huge sail, how do you get that into space? How do you unfurl it? How do you deploy a sail that's 300 meters in size or 400 meters in size? Yeah, I don't know.
It's a cool concept, and it's very efficient.
Very efficient. In terms of fuel efficiency, it's the most efficient because it's zero. It's 100%.
Yeah, the sun's doing it anyway. Yeah. You might as well hitch a ride, right? But it's really about scaling that up. I think it'd be kind of cool if you could harness some of the sun's kind of solar pressure to almost it's almost like the laser missions, right? Have you heard about that? There's a laser using lasers to fuel a light sail.
Oh, I have heard about that. Yes.
So the idea is, I guess, if you could collect solar energy and concentrate it into a laser, I mean, any source of energy to produce the laser, but then use the lasers to accelerate the sail. And I don't know if it's the same material either, but it would accelerate the sail to a significant percentage of the speed of light. Mm-hmm. You can travel to other stars because you're getting this concentrated energy, light energy pressure, I guess, photon pressure from the laser. So
I think at least what I taught in my lecture today was that. So I read some of the conceptual missions that you're talking about, where they put basically you have a laser in orbit around Earth that you shoot at your sail and off it goes, right? You accelerate it. And if you do that, you can accelerate your sails so much. We're talking tens to 10,000 or 20,000 or 30,000 kilometers per second.
That's significant,
crazy. Right? And then you could get to Alpha Centauri in a human lifetime, which is, and that's the biggest problem, right? Because if you want to fly anywhere beyond our solar system, there's no propulsion system that we have invented that could possibly make that happen. So, because it would take tens of thousands of years, right? But if you had a solar sail and you use this laser thing that they're talking about, then you might actually be able to do it. But I think we're 100 to 200 years away from that kind of technology. But whenever I hear this, whenever I read about this, Ryan, the lasers in space, all I can think about is Dr. Evil or something like that.
Yeah, I know, right? Air quotes, lasers. It's
laser. Yes.
But it's cool.
Okay.
I think that's a cool way to do things. Lasers.
Well, I'm hoping that we go for it. There's another test in space right now. There's the Planetary Society has their own light sail up right now. Mm-hmm. I think it's still operating, and I think they were showing that they could change their orbit around Earth using the solar sail. It's a smaller sail. It's 5 meters in size. It's still a little bit smaller.
Wasn't that a nanosat too, or is that something different I'm thinking of?
I think its payload is small, so it could be a nanosat. Yeah.
Interesting. That's a whole other can of worms. I mean, we can go for hours just talking about interesting new spaceflight concepts, but
yes, yeah. And instead, though, why don't you tell us about Apollo 17?
Yes, an older spaceflight concept. Yes. Very, very brute force. Put weight on rocket, fire, controlled explosion down, rocket goes up. It's perfect.
You're a rocket scientist.
Yeah, there you go. Honestly, controlled explosion. That's the best way to think about rockets in general, is you're literally lighting a bomb underneath you with the hopes that you're going to go fast enough to escape Earth's gravity and, more importantly, its atmosphere. But anyway, on December 7th, 1972 was Apollo 17. And I mean, we talk about Apollo a lot because it was this significant, very important series of missions to humanity, right? But Apollo 17 was particularly interesting to any scientist because it was the first mission to bring along a scientist, Dr. Harrison Schmitt, who are a former host and good friend. Harrison Roos is named after Harrison Schmitt. So I had to bring that up for his sake. So hopefully he's listening. It was also the longest mission to the moon, interestingly enough. And the last time that we were there. So it was kind of like, we're going one last time. We better spend the time and do the science. And so it's interesting, you have astronauts for the Apollo program who were all, test pilots, military men, selected from the best of the best pilots. And then you have Harrison Schmitt, who was a very integral part of the Apollo missions from the science perspective. There were several scientist astronauts trained, including Schmitt, but he was, a really big part of teaching astronauts, or rather teaching the flight astronauts how to do science. Now, they taught him how to fly as well. The first thing he had to do when he was accepted to be an Apollo astronaut was attend a year-long course in flight training. Because, if anything went wrong, you have to know how to fly the modules. And so he actually received his Air Force jet pilot wings, which is kind of cool. Later on, he flew helicopters as well, cool. Even after he came back from the moon. So it was kind of cool that he, he went on a flight that only, just over a dozen people in history ever got to go on. So he's had a lot more of a flight than most. But it was interesting that he had to take this big, long flight training course just to bring him up to speed with the control systems. But the really great thing that he did was teaching the other Apollo crewmen to be good geologic observers from orbit, so to identify interesting geologic targets from orbit for future scientists to study. And he also taught them to be good field workers on the ground, right? To not trample all over your samples, to the proper techniques for taking rock samples. And many of these techniques he actually developed himself. And so it was very fitting that Harrison Schmitt was chosen for this mission as well. So this is a nod to the launch of Apollo 17, but I really just wanted to focus a little bit more on Harrison Schmitt himself, who was just a really interesting guy, the first scientist to fly to the moon, the only scientist to fly to the moon, and really paved the way for astronauts today, for the 600 other people who've been to space in the last 50 years, to be scientists as well as pilots, doctors, engineers. They have to be able to do science, because that's why we're in space right now, is to do the science and learn how to keep humans alive for a longer period of time. So there you go. Harrison Schmitt was the first.
Yeah, the icon of the Apollo 17 mission. I think they were on the ground for like 2 or 3 days, weren't they? Whereas Apollo 11, the first one, they were on the ground for like 36 hours, I think, or something like that. It wasn't very long.
Yeah, it was busy, right? Very busy. Just grab, the first Apollo 11 was like grab some rocks. Take everything we can, because we don't know if this is going to work again. I mean, at that point they didn't even know if they were going to come back, going to be able to get back. But at any rate, by the time they got to Apollo 17, they had some successes. They of course had some failures as well, but they had a better idea of what they were doing, a little more careful in the choice of landing sites. The mission was a little bit more scientific, of course, with Schmitt there. So
well, that's what it takes, right? Real. You got to test out the tech first, right? If you look at the International Space Station, it didn't start doing like full on like science operations until like 10 years in. That's because it's in construction phase, and you have you're building and you're maintaining and you're getting everything running, and then once it's going and really humming along is when you really get the science. Not that they weren't doing science at the very beginning, but that's when you can really make science the priority, is when the mission, when you've worked out all of the engineering kinks and now you can do the science stuff.
Mm-hmm. And it's a kind of a good analogy for rocketry in general, right? Like you start, in the 1920s with Goddard, right? And just kind of like, okay, it literally is an explosion, and we blew up a rocket. Oh, we blew up another rocket. Oh, hey, we blew up this rocket, but it went like a kilometer up. That's cool, right? So you build upon it and eventually get something that kind of works.
What I love about what you just said is exactly what has been like watching SpaceX over the last like 15 years. Mm-hmm. It's like a modern version, because they had a whole bunch of explosions and stuff like on the launch pad and stuff. It's been fun.
That was the best part about the journey that SpaceX has taken. You can talk about other spaceflight companies and private companies and say what they've been doing, but just the coolest part of it all was just seeing it fail. That got people interested. Like, mm-hmm. I show kids the explosions still because they're hilarious, and I'm like, hey, look at this. This is how to not do rockets, but it's a good analogy for life. You go and you try something, and it fails. And this is like the hardest thing to do, right? Is to send rockets to eventually send people into space. And they went from rockets exploding on the launch pad to landing and reusing rocket engines and payload bays and doing all kinds of cool stuff that we never thought was possible. And just accepting the fact that the failure is part of that process, right?
The question is when are we going to go back to the moon?
Hopefully soon.
I think they've already pushed it back, haven't they?
2024.
24 was the initial one. I think they pushed it back already, though.
Oh, okay. That's news to me.
With the world the last couple of years, but it's still. I mean, in this decade,
it's definitely in this decade. Yeah,
I'm hopeful that at the end of this decade, we're going to look back on this as a very important time in history, when not just private industry ramps up in spaceflight, but when we actually return to the moon and kind of kick off the next chapter of human spaceflight history.
Oh, yeah.
I think it's the Martian Promise, which has sort of given the moon story a setback, and maybe it'll come up together. Martian travel, moon travel, and probably even what's the place in Jupiter's orbit, Titan. Sorry, not Titan, it's Saturn. Mm-hmm. Actually.
So man, can you imagine if we sent humans out there?
Titan or
either one, Jupiter or Saturn. If we sent humans out there, that'd be amazing. I hope they do that in my lifetime.
Yeah, that's what Netflix is for. So
exactly.
That's what Juno is for. Have you seen the images from Juno?
Oh yeah! Amazing. Oh my gosh!
Holy moly! That feels like being there.
And you know what's amazing about Juno? The Juno spacecraft in orbit around Jupiter has this camera on board that was specifically sent for a citizen science initiative. It's a camera where all of the data. I mean, it's used for science, like public science as well. But the data is made available. The hard data, the raw data, is made available to anyone, so you can do your own like imagery with it. And I think that there's even a little bit of ownership over the pointings, but I'm not 100%. Anyway, I'm not 100% certain on that.
I mean, most NASA stuff's pretty good, as long as you're using it and crediting it properly.
Oh yeah, definitely.
So it's actually cool. I've seen some friends have kind of put together some of the images.
Yeah.
Into videos and oh my gosh, they just look just so cool.
Okay, I'm gonna skip our last one because December 7th, 2018, Chang'e launched towards the moon, which was part of Chang'e 4, from the Chinese moon program. So you can look that one up. But if you're just tuning in, everybody, you're listening to York Universe. We're, of course, broadcasting live from the Alan I. Carswell Observatory, located at York University in Toronto, Canada. If you are not there, you can go to our website and log into the online public viewing. You can find us on social media. You got Jesse, you got Ryan, you got Kasitij, and we've been chatting about this week in space history. And now we're going to dive into a little bit deeper on some stories. And we're going to start with black holes, which is always everybody's, funnest.
Oh, we have good stories this week. Good stories.
Good stories. Kshitij, tell us about some black holes.
Sure, and this is definitely a good story. Just trying to play on words. So the first thing I would like to say is that the acronym IMBH, it kind of sort of rhymes with the, in my humble opinion, acronym.
Mm-hmm. And
it sort of gives me a little bit of a giggle sometimes, but that's just my observation. Anyway, so IMBH is basically intermediate mass black holes. That's the short form. And M31, our near dear neighbor, it's the galaxy wherein we have a globular cluster, and that's the story about. So we have a 100,000 solar mass central black hole apparently in that neighborhood galaxy. It lives there, and it has many globular clusters. This is one of the most massive ones wherein this central black hole has been found or discovered, or it's anticipated still with this particular paper, which was published probably 3 weeks ago. The globular cluster itself is B023-G078. The reason I'm actually getting into the boring details is just in case someone wants to look at further. Yeah, so, and then the point is, some astronomers at the Liverpool John Moores University in the UK, that's again another detail. So they have spectroscopic data, kinematic data basically, from the Gemini infrared integral field spectrometer. Again, details, but those are important details because this is spectroscopic data. So they think there is a strong rotation somewhere within that globular cluster, which indicates that there is a black hole over there, and the size of it is neither too large nor too small. The strong rotation is somewhere to the tune of 20 kilometers per second based on the objects surrounding the black hole. And there's a velocity dispersion which rises to around 37 kilometers per second towards the center of the cluster, or center of the area that they're observing, basically. So that is the reasoning, that is the science behind what they are claiming, let's say. And the accuracy claim is at a higher than a 3 sigma significance for stat nodes, or stat people, sorry, who can understand this. The category, I said,
decent. That's decent. Usually it's 4 or 5 sigma. For particle physics, it's like 4 or 5 sigma, but 3 sigma is good. That's like 99%.
Go astronomy.
Yeah, go astronomy, exactly. I think particle physics, are you saying talking about the experimental ones or the theories?
Yes.
Anyway,
yeah, experimental physicists, yeah.
Okay, that's good science and good astronomy, of course. So what was I saying? So this is, of course, an intermediate mass-sized black hole. They're very rare, and scientists or astronomers or observers seem to be very delighted with the fact that at least they have found something that unique and so close to us. And they're saying probably in the lack of active accretion, it does not even give off any light, and its mass class, as we said, is a unicorn of sorts. So the research says that the study of the metal content of the cluster puts its age at 10.5 billion years, and a metal signature which is similar to the galactic cores in our own galaxy. And then, excuse me, I think that's pretty much about the news or the sensation. And you can find out more on the ARXIV page about this paper. Didn't really come on that well, but I think it's in the details.
Yeah, intermediate mass black holes is, as you said, it's a unicorn of sorts. It's this. We can find tons of stellar mass black holes, and we know of tons of supermassive black holes, but what's it called? The lambda CDM model, the model that we use to describe how the universe grew all of its galaxies, says that there should be intermediate mass black holes in this 100,000 solar masses range, but we don't find any of them. But so I think this is either the second or the third paper that's come out in the last 3 years is seemingly proving showing some pretty definitive evidence of a intermediate mass black hole. The other one I remember, there's definitely at least one more that I know of, and they found it. It was an X-ray binary that they found, and they're pretty sure that one of them is a star, and then the other one is an intermediate mass black hole, which is a wild system just to begin with. And then this one here is
right.
This is an intermediate mass black hole at the center of a globular cluster. That's what this is?
Mm-hmm.
Yes, I think the sensation is about the fact that it's so close to us and it's right next to us, and the rest, of course, is science for those who are interested.
It makes sense. A globular cluster is an interesting place to go looking for it. As you point, so they're talking about it based on velocity dispersion, which makes sense because you can do kinematically, you can prove a gravitational source. This is how you do this is what Kepler's third law is all about, right? You can use the velocity that things move at to prove the gravity well that they're in.
Well, basically, so all these signs that Vera Rubin and the subsequent researches, which ultimately point to dark matter existence, that's the same kind of concept that's used to detect black holes as well. So if one was to get amazed by the simplicity of it, I think that's why I said I really didn't put it that well, but it's interesting, and it's hilarious that it's right next to us, and we've been looking everywhere else forever now. Of course, I mean humans have.
It's very interesting that it's in a globular cluster, right? I mean, ideas about globular clusters as cores of ancient proto-galaxies, right? And then gradually colliding together. So, I mean, if we look at black holes, supermassive black holes building hierarchically through collisions, right? Like you get galaxies crashing together and those black holes merge, and then galaxies crash together and then those black holes merge, and they hierarchically get larger and larger and larger. It makes sense that we should find intermediate mass black holes in ancient cores of galaxies, if that is indeed what most globular clusters are. So I thought that was really interesting. The other thing it got me thinking about with globular clusters is blue stragglers, right? So I didn't realize how heavy this intermediate mass black hole actually is, 91,000 solar masses. But blue stragglers are stars in globular clusters that are much more blue and brighter and hotter and more massive than the rest of the stars in the cluster, and are thought to be formed from collisions of stars, right, in these dense environments. And so I thought, well, if a blue straggler eventually did explode, it could become a black hole, but that certainly wouldn't account for the 91,000 solar masses. But it's interesting to think about the hierarchical model of black hole formation. And one other point I wanted to make quickly before I pass it off to you guys, because I know you have lots of interesting things to say, and I'm ranting. The other intermediate mass black hole discovery that I can remember was from a gravitational wave observatory from LIGO and Virgo, a collision of two intermediate mass black holes, although they might have been low. They might have been not in that 100,000 range, solar mass range. They might have been more like a couple dozen solar masses. So
yeah, they're like, but I still think that's telling, right? Because those, like, you don't get. So when it comes to like when you get a black hole, sorry, I got to gather my thoughts here. When a black hole, when a star explodes, and you make a black hole out of that, like, you're not making a black hole that's a couple dozen solar masses. Like, that's too big of a star, or at least you shouldn't have that frequently. So if you're finding a black hole through gravitational wave experiments that is like, say, I don't know, 50 or 60 solar masses, then it's likely that is a merger of some kind, right? And
likely, yeah.
Therefore, you are on the pathway to building the ones that are like 100,000. So the only question that I have left with all of this is, so research is starting to show that intermediate mass black holes do exist. They're unicorns, but they do exist. The question is, why are they so rare? And I guess it has to do with growth is quick. And so you can make little black holes and they'll grow, but there's a gap between, they'll grow to, I don't know, whatever they grow to. No, wait, this doesn't make sense, because you're going to have different formation scenarios for supermassive, and they're not linked Okay, I'm just ranting at
Not
this
necessarily. I mean, there's
No, but then you're probably thinking in the right direction, because
yeah.
the little that I read about extragalactic astronomy, I think it does boil down to surface physics in a sense, because small is easy. The large ones, of course, because it's too massive, and maybe the intermediate ones really need the right conditions and the right sustaining conditions for them to even stay there. And even this paper, which I didn't really fully cover here, it says it's a stripped galactic nucleus which ended up making this intermediate size. So anyways, I'm just adding to what you said. So it's in the right sense.
It's a cool paper. And I also note that just a funny thing when you said Liverpool John Moores University, and when you said John Moores, I just thought of Dr. John Moores.
I thought of it, and I Googled it, and I realized
a different
that's
John
not
Moores.
it. It's a different John Moores.
Okay,
Maybe
let's do. We got 9 minutes left. Let's do a quick couple of stories. So I'm going to quickly mention this story because I think it should be on everybody's mind all the time, and that is mega constellations. So there's a paper that came out of the University of Regina, which is here in Canada, and by Dr. Samantha Lawler, and basically what her and her teammates did in this research paper is say, okay, SpaceX is going to launch some mega constellations. Amazon's going to do it. China's going to do it. And there's a couple others that are going to do it. What is our sky going to look like, given what we know about these mega constellations? And they have some good data on the current satellites already in orbit from Starlink, right? Because SpaceX has been launching Starlink for a while now. And there's already 1,000 satellites up there.
Thousands.
Yeah, there's a bunch, right?
Yeah.
So there's good data on what the Starlink satellites actually look like, how reflective they are, how visible they are from different latitudes, et cetera, et cetera, et cetera. So what they did is they did a whole bunch of simulations based on the expected orbits of the completed mega constellations that are currently on the books, meaning have their orbits registered. And what they found is just terrible. The simulations are terrible because they show that once these satellites are up, in the ones in the paper, it's I think 4 or 5 mega constellations. We're talking something like 65 to 70,000 satellites, which is mind-boggling.
Okay, amazing.
Mind-boggling. Like right now there's only 5,000 satellites or 2,000 satellites in space or something like that. So they simulated it all, and they found that at the peak, once all of these are up, if you went out to a really dark sky and you wanted to do some stargazing and you looked up, roughly 1 in every 15 visible points of light would be a satellite, which means it would be moving. So if you just try and close your eyes and try and visualize that for a second, that's no longer just a enjoyable night sky. That's a traffic jam above your head.
Allow me to say something wise.
Yeah, go ahead.
Buy planetariums of all kinds.
Yeah.
You have live planetarium right in front of your eyes.
Yeah. That's the home run of that paper. You can go read the paper, and they made their simulations available where you can for your own latitudes and your own location on the Earth. So they're all open source, and they have websites set up for it. But the conclusion really is that if we let these big companies do whatever they want in space, then we are going to destroy a natural resource, both astronomically, research speed, telescopes will have trouble looking through this traffic jam of satellites. But also, we won't even, it won't be the same going out to watch a meteor shower or the Northern Lights, because it'll just be whizzing lights up there all the time, and it's not the same. So it's a shame. It's good that the paper has been done, and we can see the results and we can see what we need to fight for. But really, the only way that anything's going to change is if we put pressure on our governments to regulate these big companies, and who knows if that's going to happen.
I think the implication that is pretty imminent is that we wouldn't be able to fight with people on the ground anymore for, let's say, less light pollution or use separate kinds of light. We literally will be talking biggies, and they wouldn't listen to you, of course, so you really can't change anything anymore once they have been launched.
Yeah.
Scary.
So that's the story.
All right, we have 5 minutes.
We have
I'm going to
5 minutes.
make
You
one
think
point
you can
about
do
your
it, right?
story. I'm going to make one point about your story, then I'm going to do my story.
Okay.
The point I want to make about your story is that a lot of observing astronomy science is done with long exposures. So as soon as you put a long exposure up, you see the trains of not just the one satellite that went through your field, but every satellite that goes through your field of view over the course of your observing run. And that amplifies it by a lot.
Mm-hmm.
Anyway, last story of the night. I've got to do it quickly. We talk about where Earth's water came from. And there are many theories about that. Well, several hypotheses. Was it comets crashing into the early Earth and bringing water? Was it wet asteroids? Was it small planetesimals that formed part of the Earth as well and brought water? Was it hydrogen that was already in the Earth's crust mixing with oxygen? Was it the collision of the moon that crashed in, or the collision of the object Theia that created the moon that added the water? So all of them have different evidence to support them, but here's a new one. The biggest challenge is kind of explaining how Earth got its water. We know it didn't get its water when it first formed. It formed closer to the sun. Higher temperatures made sure that water was not condensing. It was water vapor. So farther from the sun, water would actually condense, form ice crystals, become part of asteroids and comets and larger planetesimals. And so, of course, the leading theory is that these distant bodies, comets, asteroids, and planetesimals, crashed into Earth after it formed, melted all the icy water, and then that water was Earth's water, and that's what we get. However, there's a bit of a problem. If we look at what's called the isotopic composition of the water on Earth, isotopic composition is basically how much normal water compared to how much heavy water. Heavy water has an extra neutron on one of the hydrogen atoms. It's called deuterium. So the ratio of heavy water to normal water should be pretty much the same on Earth as in these distant comets and asteroids, if that's where Earth got its water. But it's not. These so-called C-type asteroids in the outer solar system, their ratio, their isotopic composition, the amount of deuterium they have, is actually quite a bit more than what the Earth has. So this means that there must have been, these C-type asteroids could have been a source of water on Earth, but there must be another source. And so this new research from an international team of scientists proposes that the solar wind actually created water, atom by atom, on the surface of tiny dust grains in the solar system and eventually the larger rocks, forming this isotopically lighter water with less deuterium, more normal hydrogen with its proton. And that is what provided the Earth with the rest of its water. And so what they actually found is that there's a process for this, that the solar wind, which is made of what's called hydrons, which is just literally a proton, an H plus ion, in the solar wind, it irradiates little silicate minerals on the surface of asteroids and actually creates new water molecules. And so this research is actually based on an analysis of an asteroid called Itokawa, which was visited by the Jackson mission Hayabusa, and had samples returned in 2010. And what they found when analyzing the sample was that the first 50 nanometers of the Itokawa asteroid contained enough water where the density would be equivalent to about 20 liters of water for every cubic meter of rock. That is a huge amount of water.
Whoa.
And so this might be enough to explain where Earth got the rest of its water, the rest of its light water.
What?
And the last point about this, because we're almost out of time, is that processes like this likely happen on other asteroids and solar system bodies, so astronauts could use that as a source of water in the future. Very cool.
It is a shame that we don't have enough time to dig into that. That is.
I know. I wanted to discuss it. Well, that's
cool
okay.
Story.
We gave you just the facts, but it's really...
Well, everybody, you have been listening to York University Astronomy and Astrophysics program, written and presented by all the cool people that have ever been affiliated with York University. You've had myself, Jesse, Ryan, and Kashitich tonight. Stay tuned because there's a great lineup of Canadian astronomy. There's Quirks and Quarks, Western Worlds, and Science for the People, and you can always find us on all the great social medias. And we also have a website, observatory.info.yorku.ca. Thanks for coming, everybody, tonight.
Good night.